And we're back. Welcome back from Tuesday. Today we will continue on with our conversation concerning confidence intervals. Hopefully finish up the module. If not, then we can certainly carry the balance of this on Tuesday. Before we begin, let's take care of some administrative information. And so all of this material is in Chapter 9 of the main text, Probability and Statistics for Computer Scientists. The material on method of moments and max likelihood estimation are from Section 9.1, and the material on confidence intervals, which we'll talk about today, is in Section 9.2. The project that is due, it was originally due on the 13th of April, which is this coming Monday, but that has been postponed for one more day. It will be due on the 14th, which is this coming Tuesday, the 14th of April, due at the usual 1 second before midnight, 11:59 to 59 seconds. Easter recess is from the 10th, which is Friday, through the 13th, which is Monday. So I've adjusted that in the Blackboard and also posted on the Slack channel accordingly. Okay, so where we last left off, we talked about, let me switch pens here. I think blue has been working. Where we last left off, we talked about the idea that when you calculate an estimator for some unknown ground truth parameter, this estimator is a function over data. And the example we used was the Poisson distribution and the estimator, whether it's max likelihood estimation or method of moments. The expression that we got, the statistic function over data for lambda hat, is x bar, the sample mean. And Poisson, by the way, is one of those distributions for which the method of moments and max likelihood give you the same statistic, x bar. So if we replace this lambda, the parameter for the Poisson, with x bar, we do that over data, and we acquire that data through sampling. And by the sheer nature of stochasticity, when you sample from one sample to the next, certainly those data points that you sample, those observations, they're going to be different from one another. They're going to vary. And therefore, the statistic you compute over them will also vary. Now, in that case, we want to know how much will it vary, and that's what the standard error gives us, the amount of how much this statistic varies. And if it varies less, it's going to be more reliable. If it varies more, it's going to be more unreliable. And so the standard error is nothing more than the standard deviation, and we designate that name standard error as a note to the reader, or the listener, so to speak, that the particular standard deviation we're talking about is a standard deviation of something that is itself a statistic. And so we tried to compute, and we went over this last time, two different methods we explored for how you might compute the standard error for a statistic. We started out with one approach. We made use of the first and second moment for the Poisson. So there's the first moment, and this is the second central moment, more correctly. And on the left-hand side here, we had one approach where we measure this variance and we substituted in what we knew about the moments, and then we solved and ended up with this expression. The standard error of x bar is the radical of the sum of all the samples upon n. Another alternate approach we used is we made use of the sample variance, S squared, the unbiased version of the sample variance. And we made the assumption, of course, that with this unbiased version, we're going to take the square root of it, and that'll give us the sample standard deviation S. And so the S squared that we make use of here is 1 over n minus 1. The sum for I goes from 1 to n, the number of samples, xi, our samples, minus x bar, the sample mean quantity squared. So we took our expression for the variance of x bar, and then we took the square root of it, and that gave us sigma over radical n. So then for sigma, the alternate approach we took was to take the square root of s squared. There's our s squared, the unbiased sample variance. And we did a little bit of algebra, and we ended up with this expression. Now, in both of these, you could certainly calculate them, but they're a little bit messy to do. And so we'll look at so-called bootstrap methods, i.e. methods that are calculated from the data, a data-intensive method for looking at the standard error for your statistic. Okay, so these are so-called confidence intervals. And we're going to go over this with the sampling distribution of the statistic and then show you where the standard error fits in, and then also where the ground truth parameter fits in as well. So we have some distribution, and that distribution is governed by an unknown parameter. So there's our parameter. And the whole point of an estimator theta hat is we're going to calculate the theta hat by method of moments or max likelihood, and we're going to substitute that for the unknown ground truth parameter. And so this distribution is responsible for defining all the values we could possibly observe. And the problem that we had is that we have no way of knowing what is the ground truth parameter that's responsible for this distribution giving us the values that we observe. So we're going to estimate this theta hat, this statistic over the data, this estimator, and we certainly use it as a replacement for our unknown ground truth parameter. So for example, carrying this example with the Poisson distribution describes a system, a stochastic system, that where we observe a number of events over time and we don't know and we will never know lambda, the rate parameter. So what do? We estimate lambda using MME or MLE, and we get an expression, a statistic, lambda hat, okay, that's X bar. And we then keep sampling from our temporal data and calculating this lambda hat. And so earlier in the semester, we talked about this system that you use to instrument the doorway, the entry box of a retail establishment, and you're literally counting the number of people that enter the store and the number that leave the store. And so certainly you could talk about the number that enter using your rate, the number that leave, or you could subtract the two, and the difference is going to be the number of people in your store at any given moment of time. So you take these samples, and at some initial time we're going to call T0, you take n many samples. Now n could be 100 samples, n could be 10 samples, it could be 50 samples, it doesn't matter what it is. They're just some observation of the number of people that arrive in the store over successive windows of time delta t, which themselves could be 5 minutes, 1 minute, 10 seconds, 10 milliseconds. And so each one of these will be maybe, say, 3 people entered the store, maybe the next sample, 5 people, etc. So we sample n many times, and the samples correspond to the samples that are begun at some initial time t0. And maybe every 10 minutes or every 20 minutes, you're going to sample the number of people, events observed in some delta t over 100 many times. And so here, if we look at these variables, the subscript, the first number in the subscript, that represents the time instant. So the first time instant, we're going to take 100 samples. And the second index for our variable represents the sample. So x0, 1 is the first sample in the 0th time instant. 0, 2 is the second sample in the 0th time instant. n, 0 is the nth sample in the 0th time instant. Okay, so we take these 100 samples and we compute our lambda hat, and we're going to call that lambda 0 hat because it's the lambda we compute by calculating x bar, the sample mean, using all of those samples from that 0th time instant. So this is our x bar we calculate, and we're going to call that lambda 0 hat. Okay, so now maybe some time later, maybe 10 minutes, 15 minutes, time t1, we're going to take n more samples. So this would be for the first time instant, the next time instant, that's the time instant. This is the sample. So this would be the first sample in the first time instant, the second sample in the first time instant, third sample, first time instant, up to and including the nth sample in the first time instant. So these t's, t0 and t1, maybe this is at time, initial time, 0, and maybe this is 10 minutes later. And then next we're going to have another 10 minutes later, so at time 20 minutes. We're going to take n many samples. And if n is equal to, say, 100, that would be 100 samples at the beginning, another 100 samples 10 minutes later, another 100 samples 20 minutes later, and so forth. So we take n many more samples at time instant t1, and then we compute x bar from these, and we're going to call that lambda 1 hat. Okay, so this lambda 1 hat is a result of computing the statistic x bar from these n many samples, and we're going to call that lambda 1 hat the estimator that we calculated from this next n many samples. So we do that again and again and again, and here we have the nth time interval. We're going to compute or take n many samples, and from that we calculate x bar again, and then we call that x bar our lambda m hat. Okay, now certainly if we look at each one of these lambda hats, well, from one interval to the next at 0, 10 minutes, 20 minutes, 30 minutes, etc., each one of these n many samples are going to be a little bit different. So maybe you might have some of the same, some repetitions, but as a set of n many samples, they're going to be different from one another. So if they're different from one another, that means that the lambda hat that we calculate, they're going to be different from one another, not equal to. And that's the case for all of the m many lambda hats that we calculate, each one of which was calculated using x bar on these n many samples. So if they're a little bit different from one another, something reasonable that you might want to do is to look at the distribution over each one of these statistics outcomes lambda hat. So let's do that. We call that the so-called sampling distribution for lambda hat. And we call it the sampling distribution because each one of these lambda hats was obtained by sampling. And so here we have the sampling distribution for lambda hat. Along the horizontal axis, we have the values of lambda hat. So maybe right here, that's the value of lambda 0 hat. And maybe right over here, that's the value of lambda 1 hat, for example. Now, if we calculate the distribution of each one of these lambdas, and I'm going to select a different pen color. Let's select cyan. If we calculate the distribution of all of these statistics lambda hat, well, it might look something like this. And there's an observation here that I want you to pay attention to. You know, this is kind of bell curve shaped. Now, it's bell curve shaped because if you think about what happens with x bar, well, x bar is nothing more than a scalar, 1 over n, times the sum of all the x's, all of the samples, x1 plus x2 plus x2, 3, etc., plus xn. Now, the central limit theorem tells us that when you have some function that involves a sum, and certainly x bar does, well, the distribution of it is going to be normal, okay? And that's why you have this bell curve shape. Now, for this sampling distribution for lambda hat, it has a mean because it is a distribution, and that mean is the ground truth lambda. Now, this ground truth lambda is the mean if you have sufficiently enough x lambda hats in your distribution. But this ground truth lambda sits somewhere within this distribution. Ideally, it's the mean if m is big enough, if this m is big enough, but we do know for sure that it's sitting somewhere in there. Somewhere among all of the sample versions, lambda hat, this ground truth unknown lambda is going to reside. And so if the variability of the sampling distribution for lambda hat is narrow enough, i.e. the standard error is smaller, then you can say, aha, this particular statistic, lambda hat, is going to be more stable. Okay, it's more stable because if it varies less, and we know that the ground truth lambda sits somewhere in there, that lambda hat, because it varies less, is going to be more reliable. So we have a mean of the sampling distribution. We also have a standard deviation. The standard deviation of this sampling distribution for lambda hat is also known as the standard error, and that's our dispersion. And so using the so-called bootstrap method, continually sampling from the data. Let me change my pen color back to blue. By using the sampling distribution and continually sampling from the data and calculating lambda hat, you can induce a distribution and measure the standard error for that sampling distribution and actually report that as a way of talking about the stability of that estimator. So that's a lot easier to do than it is sometimes to calculate. And in fact, if you're given a data set, what do? You subsample, uniform at random, you subsample from your data, sample with replacement, and then from one sampling to the next, it's called the bootstrap sample, you're going to compute a lambda hat, and then you plot the distribution of that lambda hat and measure the standard deviation. So that's a numerical way or mechanized method that you can use to get a sense of how stable that estimator is. Okay, so you have a single estimator, theta hat, of a population parameter. That's what you do when you compute lambda hat once, right? It's a single estimator. And that estimator is certainly never correct. You'd like it to be as close as possible to the unknown ground truth parameter, theta, but theta hat, a single estimator's outcome, a value that you calculate over the data, is never correct. So it's different. Now, let's define the error as being the difference between what you have and what you want. So what do we have? We have our theta hat. In the case of a Poisson, that's lambda hat. But what you really want is theta. In the case of the Poisson, what we really want is lambda. So you have the estimator, but you really want this unknown ground truth parameter. So the sampling error is the error in a statistic that you get due to the fact that samples are different from one another. Because in calculating this theta hat, you calculated that using some function over your samples, right? You input, that might be X bar, might be something else. And because these samples are different from one sampling to the next, well, the outcome of this function, i.e. your statistic, your estimator, is going to be different. So the error in this statistic is due to the fact that samples are often different from one another from one round of sampling to the next. So one of the questions that we set out to ask then is how much trust can you invest in a given statistic? You kind of need to know that, right? The same way we talked about unbiased and consistency, well, we need a way to ask the question or to answer the question, how much trust can we invest in a given statistic theta hat? So this trust idea is given by what's known as a confidence interval. And what this confidence interval does, it expresses values of a statistic that they can take on when you calculate them and the associated confidence. And it's a way of measuring this idea of how far off or how typical a value is relative to all of the possible values that the statistic can take on. So let's go to the definition. A confidence interval is as follows. It's an interval, so that means it's a set of numbers. And it's on the closed interval, and let's assume A is a real value. It could be an integer, depending on the parameter you're trying to estimate. But it's an interval, a closed interval, so we include the endpoints. So if you have a number line, you have a value A, and you have all the real values up to and including B, if we're talking about real values. So it's an interval or a set of values that your statistic can take on. And we say interval AB is a so-called 1 minus alpha times 100, and that is a percentage. So this interval AB is a 1 minus alpha times 100% confidence interval for some parameter, that ground truth parameter theta, if it contains a parameter with some probability that's 1 minus alpha. So what does that mean? Here we have a distribution, and that's the sampling distribution for some parameter theta. Okay? Well, the sampling distribution is sampling distribution of a statistic. Now, we have this distribution. Let's say it looks like this. And floating somewhere is the ground truth theta. We just don't know where that theta is. I'll put a question mark. So that ground truth theta is somewhere in this interval over which the distribution is defined. Now, each one of these values, that might be theta 0 that we compute, maybe theta 1 hat is there, theta 2 hat is there, and maybe ... theta m hat is there. So we get a distribution for our theta hats, our statistic. So if we have an interval, we say, all right, well, here's A, there's A, and there's B, and we say that interval AB is a 1 minus alpha confidence interval. Let's say alpha is equal to 0.05. So that means if alpha is equal to 0.05, and we actually choose alpha, 1 minus alpha is equal to 1 minus 0.05, which is equal to 0.95. You take that 1 minus alpha, you multiply it by 100, so that's 0.95 times 100, that's equal to 95. So if alpha is equal to 0.05, it's a 95% confidence interval. And an interval AB is a 1 minus alpha times 100% confidence interval for some parameter theta that's unknown if there's a probability of 1 minus alpha that this parameter is going to fall within that range between A and B. So what does that mean? It says if we were to take the area under the curve for the sampling distribution for theta hat, well, that's going to be 95% of the probability mass. And since probabilities integrate to 1, that's going to be 0.95 of the probability, right? The integral of that, or 95% of the total probability mass, is going to be the area under the curve for which that range, that area interval between A and B is responsible for. Okay? So that's what a confidence interval is. Now you'll note, it's really important to note that I said parameter theta. I didn't say theta hat. We know that this theta is floating around somewhere. It's valued. It might be here, it might be here. We don't know what it is. But we can put a kind of probabilistic bound on it, a probabilistic estimate to say, I'm pretty confident that it's somewhere in here, right? And so that's what confidence interval does. It tells you this reliability, knowing full well that you don't know what theta is, but you can say with some degree of assuredness, it's within some interval. And you get that from your theta hats distribution, not from your theta. You don't know what theta is. Okay? All right. So confidence interval, again, is interval AB. We say AB is a confidence interval. It's a 1 minus alpha times 100% confidence interval for parameter theta if it contains the parameter with a probability 1 minus alpha. Okay. So if alpha is equal to 0.05, we refer to this AB as a 95% confidence interval. And typically, you choose what your alpha is in practice. Okay, so what exactly does this mean? Well, with probability of 95%, theta will have values within this interval. You can think of this distribution, to think of this a little bit in an alternate fashion. You have that distribution, and that's a distribution for your theta hats, which you can calculate. You have ground truth theta in here, and ground truth theta is somewhere. You just don't know where it is. So if you choose AB the right way, AB, essentially this is like saying, okay, well, theta is somewhere in here. You could kind of draw it this way and say AB, and now you're asking the question, does AB cover theta? Theta could be somewhere over here, theta could be somewhere here, theta could be somewhere here. Is this theta covered by that interval AB? Because theta is just the value, the ground truth parameter. So you can say confidence interval is kind of this covering probability. With probability of 95% for alpha equals 0.05, we say that we'll have theta will have values that's in this interval. This interval, 95% of the time, will cover the value of theta or include the value of theta. So that's what a confidence interval is, and that's what it means. All right, so with 95% probability, 95% of the time, you kind of know what the values of theta are. You don't know its exact values, but you know the boundary within which these values of this unknown quantity will occur. Okay, so it's like kind of knowing. We kind of know with 95% of the time that it's going to be in this sandbox, so to speak. Okay, so let me ask you a question, and I'm going to ask you to pause the video and then think about it and answer the question. So we have two scenarios, and the question is, for which of these scenarios you're more confident? We have two different securities or stocks, and first scenario is we have an average stock price theta 1, and we know that theta 1 was in the range. You don't know exactly what it is because you don't know the ground truth average stock price, but you know it's in the range between $12 and $32.5 per share, and that range covers it 65% of the time. So that means theta 1 is the average share price, and theta 1, we don't know what its real price is, but we do know that if we take that $12 and we take that 32.5, there's going to be theta 1 is within that range between 12. Oops, let me draw that a little bit better. It's going to be in that range between 12, 32.5. We know it's going to be 65% of the time. Okay, so that's our first scenario. Our second scenario is we have another security, that's security 2, and its average stock price, share price is theta 2. It's unknown, so this is the ground truth average share price, and it's going to be somewhere within that range between $13 a share, so let me write 13 on the low end, and $37 a share, 37 on the high end, and that's going to be 95% confidence. So we say that 65% of the time, security number 1 is going to average between 12 and 32.5. It's going to be covered, and 95% of the time for security 2, it's going to be covered by the interval between 13 and 37. So which of these are you more confident in? Are you more confident in the first one or the second one? So please press pause and think about it, and we'll come back in a few moments. Okay, we asked the question of which stock price are you more confident in? Well, one of the things you could do is say, okay, well, I know that this event, this covering, will include theta 65% of the time. So that means 35% of the time is not going to be in this covered by this interval. Now, this interval just happens to be, say, 12, call that 22, 32, 20.5. So that difference is going to be $20.5 to get from 12 to 32. Okay. And this interval is going to be what? 13, 23, 33, 37. It's going to be $24 range. Okay. So we know that for the first security, the range of values it can span, theta can swing from low to high about $24, right? In the first case, it can swing from low to high $20.5. Okay, so the first one swings more, all right? The second one swings less. But for the first one, 65% of the time it's in that range. So that means 35% of the time it's going to be less than 12, or greater than 32.5. So even though we know 65% of the time it's going to be in this interval, 35% of the time it's going to be outside that interval. Likewise, for the second one, well, 95% of the time it's going to be in that interval, so 5% is going to be less than 13, or greater than 37. I scribble 37. So you would say that even though the second security swings more broadly, 24, it swings by $3.5 more in terms of the range of values, you can count on it more to be within that range because its confidence interval is 95%. So if you are going to invest, for example, you know that it's a more rare event for the second security to be in this region or in this region than it is to be in this region or this region, so more rare, right? It's more common for the first security to be outside of the bounds of this interval. So if you were going to invest, you could say, oh, well, the second one is more stable, okay? But you could also use this 65% to your advantage, because if you know at the moment that the first security is, say, $10, right at the moment, you know there's a 65% chance that it's going to be between 12 and 32. So you might say, okay, well, let me wait until this swings really low or really low beyond or below the left-hand bound of this confidence interval. And then I'm going to invest because I know at some point it's going to hit this interval. And then once it jumps into this interval, you say, okay, well, let me go ahead and sell and then pocket that small difference. Okay. So for this scenario, more confident in the second alternative, but I might want to invest in the first one and actually take that 65% to my advantage to make a little bit more money. Okay. And so why are we more confident? Well, what could you do or would you do with this information? I kind of got ahead of myself. Well, you could use the fact that there's a 35% chance for this first security to be less than 12 or greater than 32 to make a little money. Rely on those swings, if you will, that volatility or the unstableness to your advantage. Okay, so we have our confidence interval. Let's take a look at what this means mathematically. So we said the confidence interval, AB, is a 1 minus alpha times 100% confidence interval for some parameter that's unknown, theta, if it contains the parameter with that probability 1 minus alpha. So that means the cumulative distribution, the area under the curve more correctly, between those intervals A and B has to add up to 1 minus alpha. So if this is A and this is B, we actually want the probability, the area under the curve, for this interval, right? And that probability, that total probability, the integral of P of X, has to equal 1 minus alpha. That's what it means to be a confidence interval. So mathematically, that's what we do. And population parameters are not random, right? Population parameters, they're constant. They remain the same. And this, because the samples change that we get from this population distribution governed by that population parameter, we know that the population parameter estimates, the lambda hats, are stochastic. And so the interval AB is stochastic. And if it's stochastic, we need to talk about a probability of coverage because we don't really know what this data is. We don't know what the ground truth is. We know it's somewhere in there, but the thing we can measure is going to change. So we look at the distribution over the thing that can change, this lambda hat, and then we look at how likely it is for that unknown theta to fall within the value. And the reason why we can do that is because theta does not change. It is a constant, but we just don't know what it is. So here, floating around somewhere within this distribution is going to be our ground truth population parameter. In the case of a Poisson, it's lambda. Okay. So this is in the book, figure 9.2. Let's set the pen to blue. And this represents confidence intervals for the sample parameter theta obtained from samples of data, or different samples of data. And so you have your ground truth distribution, some distribution, like the Poisson distribution. And that Poisson distribution has some ground truth lambda. It doesn't matter what it is. You could say this is equal to 7. You just don't know what it is. Okay. So now for this Poisson distribution, at some time t0, you take 100 samples, for example, x1, x01, x02, x0, 100. So you take 100 samples. So for that 100 samples, you could absolutely compute a lambda hat. And if you can compute a lambda hat from it, you could subsample from this 100 and compute different versions of lambda hat. So you could subsample from this. Maybe you take 30 of them and you compute a lambda hat. And then you take another 30 by sampling uniform at random and compute another lambda hat. and then you do that again and again and again, well, all of these lambda hats will form a distribution, and you calculate the confidence interval A, B for that. So that confidence interval AB is depicted here with these two bars here. The low end is A, and the high end is B. Okay, so that's one of these. So let's call that A, and let's call that B, and that's what you get from that round at T0 when you took 100 samples. So now at time T1, you do the same thing. X, that should be a T. At T1, you do the same thing. That's X1, 1, X1, 2, up to and including X1, 100. So you take this 100 samples, and you could compute an X bar, or, as we did before, we will subsample 30 of them, of this 100, uniform at random, compute lambda hat. We take another 30 subsample, uniform at random with replacement, compute another lambda hat. We do that again and again and again. We get a different distribution, right? Because these were from different 100 samples, and we're subsampling 30 of them each time. 30 of the 100 here, 30 of the 100 here. So because we get this distribution of lambda hats, it's a different distribution. Maybe this distribution looks like this. It's more squashed down, and we get a different AB. Maybe AB are more dispersed here. That's A, that's B, and that's going to be here A, B, right? And that's going to represent A here, B here, and that's going to be resulting from T1. Okay, so we do this again and 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 again. The mth round, and that mth round, again, we take our samples from the ground truth distribution, X, M, 1. We take 100 of them. In this example, XM, 100. Again, we subsample 30 of these and then compute our lambda hat. So we'll subsample 30 of them, calculate lambda hat. We do that again and again and again, subsampling another 30, compute lambda hat. We do it some number of times. This gives us another sampling distribution for lambda hat. It looks a little bit different. We calculate the confidence interval. So that's A, that's B, and we depict that as this interval, A, B, whatever that interval is. We actually represent this A is a number, B is a number, depending on the confidence interval. And that would be for time instant Tm, that would be my A, and that would be my B. So essentially what we get for each one of these rounds of data that we get from our ground truth population distribution with unknown parameter lambda, I'm just showing it to you, we don't know what lambda really is, we get some sample 100 times, and then we use this 100 to bootstrap different lambda hats. We subsample 30, uniform at random with replacement. For each of those subsamplings, we compute a lambda hat, which is just our sample mean X bar. We get a distribution, compute that confidence interval for the distribution, and then we report it. Now, what this confidence interval measures, when we say a 95% confidence interval, what we're saying is that for 95% of these intervals that we calculate, our ground truth theta will fall within this interval. Okay, that's what the 95% confidence interval means. And we're going to try this in MATLAB so you can actually see that it really does work. This is to reinforce that the theory does work. Okay, all right. So it just so happens in MATLAB there's a function. It's in the statistics and machine learning toolbox called param_CI, and it will actually calculate the confidence interval for you. If you call param_CI on that distribution, it will actually give you the 95% confidence interval. So alpha, in that case, alpha equals 0.05. You can also call value, where this value here is your alpha, right? And if you give it the alpha, it'll actually compute that 1 minus alpha times 100% confidence interval. Okay? And so we'll take a look at that, and we'll also take a look at not just using MATLAB's confidence interval routine or API call. We'll actually show you how to calculate that confidence interval yourself. Okay, and it just so happens, if you're looking at this and you see fit distribution is computing an estimator. Okay, if you're curious about that. All right, so with that, we will end there, and we'll pick up next time with our MATLAB. Again, a reminder that Project 4, this is a typo in the slide, Project 4 is not due on the 13th. It is due on the 14th of April, and that day is a Tuesday because the Easter recess, we have Friday, the 10th of April, and we have Monday, the 13th of April. That's at DSU, Easter recess. So we will not have anything due on the 13th. I have changed the due date to reflect that. It's due on the 14th and not the 13th. This is a typo. So with that, I will see you all online. I will see you all on Tuesday, and we will end there. See you then.